Okay, Assalamu alaikum, everyone. So today we are going to start paper 4, that is the structured questions of from A2, and it's May-June 2023, paper 4-2. Okay. Let's start with question number 1. Okay, in this question, there is no choice. You have to attempt all the questions, and it's the lengthiest question paper, around 2 hours and 100 marks. Question number 1. Group 2 carbonates decomposes when heated to form metal oxide and carbon dioxide. Okay. So group 2 carbonates means they are talking about, uh, magnesium carbonate, calcium carbonate, barium, strontium carbonate, barium carbonate, right? Suggest a mechanism for the decomposition of the carbonate ions by adding two curly arrows. Okay. So carbonate ions turns to form carbon dioxide, and the oxide ion is released, which is when bonded with the metal. Okay. Now, so see, as carbon dioxide is forming and one oxygen is left. So if you see over here, there is a lone pair to the one oxygen atom, which is having a single bond, like so. If I make a arrow like this over here, so it means this oxygen is form a double bond over here. If this oxygen forms a double bond over here, so at that time, what carbon oxygen bond will do, that this bond would be broken hydrolytically. So this oxygen is this one, which comes out as a O2 negative, and this part is this, which turns into carbon dioxide. Okay. So for 1 mark, you need to put the arrow. So I did it. Now, next part. Describe the variation in thermal stability of group 2 carbonates. Explain your answer. Okay. So you have to describe the variation in the thermal stability. So if you recall the thermal stability of group 2 carbonates increases, right? And the trend is it increases down the group, right? Okay. So why the thermal stability increases down the group? As down the group, the cationic size of group 2 elements increases, and uh, so the it increases, and if you recall, due to this increase, the ion polarization becomes less. That there is a uh, decrease in the ion polarization, which makes carbon-oxygen bond more stronger, and as a result, the thermal stability increases. So, cationic size of group 2 elements increases. As a result, the carbonate ion gets less polarized, making carbon-oxygen bond stronger. And as the carbon-oxygen bond gets stronger, it's more thermally stable. Is this clear to all of you? If anyone of you has any query regarding this, please ask. Then define lattice energy. Okay. So the definitions, as I have told you earlier, you have to remember them. It is the enthalpy change when one mole of an ionic solid is formed from gaseous ions, right? Under standard conditions. So if the reactants are the gaseous ions and those gaseous ions, reacts to form 1 mole of an ionic solid. So whatever the enthalpy change occurs during this reaction, this formation of an ionic 1 mole of ionic solid from the gaseous ion is under standard conditions is called lattice energy. Is this understandable to all of you? Okay. Now, part 2. The lattice energy of group 2 carbonates becomes less exothermic down the group. Okay. Yeah, they become less exothermic down the group. The lattice energy of group 2 oxides also becomes less exothermic down the group. Okay. The enthalpy change, the lattice energy of metal carbonate and metal oxide changes by different amounts going down the group. Okay. So just how the standard enthalpy change of decomposition for group 2 carbonates changes down the group. Explain your reasoning in terms of the relative sizes of anions and relative changes in the lattice energy down the group. Okay. So as the thermal stability is increasing, so what happens to the change of decomposition, the enthalpy change of decomposition? As the thermal stability is increasing, see what they are saying that the lattice energy for metal carbonate becomes less exothermic. Okay. They are saying that this is becomes less exothermic. They are saying that oxide also becomes less exothermic. Okay. So this is for carbonate and metal. Okay. But they are saying that these two changes occurs with the different amounts. So just how the standard enthalpy change of decomposition of a reaction of group 2 carbonates. Enthalpy change of decomposition reaction for group 2 carbonates changes. Okay, so it means they are here talking about this reaction when metal carbonate on heating turns into metal oxide and carbon dioxide. That's what they have been asking for its enthalpy change. So, and here, it's when a metal gaseous ion and a carbonate gaseous ion reacts to form metal carbonate solid. So this becomes less exothermic, that's they are saying. In the same way, when a metal gaseous ion and oxide gaseous ion also form solid. So this enthalpy change also becomes less exothermic. So on the basis of this, if you see, as we move down the group, the thermal stability increases. And if the thermal stability increases, so it means this enthalpy change reactions become more endothermic, the more energy it needs, right? So we are going to write that the enthalpy change of decomposition of metal carbonates gets more endothermic, right? Or you can say less exothermic. Because as we move down, we need more temperature to break that carbonate into or decompose that carbonate. So it will become more endothermic. Or you can write more positive. Instead of more positive, you can write less positive. So this is what we have stated that what is happening. Is this understandable? Now we have to explain this. Explain your reasoning in terms of relative sizes of anions and the relative changes in lattice energy down the group. Okay. So if you see, these are the anions, right? One anion is carbonate. And if we see that the carbonate has, for example, this size, and the another one is a oxide ion, and it's very small, right? Till here, is this understandable to all of you? Mariam, the decomposition becomes more endothermic. It is because of this. We have studied this. We discussed this reasoning in the lattice energy. We discussed it already. That is the information that you guys need to know. That if I'll show you notes, then I think it will be more understandable if anyone has any confusion in this. So see, that's what we have discussed. See, that is the trend. This trend you have studied in your AS level, and in A2 we discussed this trend that the thermal stability is increasing down the group. So what does it mean? It means that as we move down the group, we need more energy to decompose that carbonate. Okay. That's what this means, that if the thermal stability increases. So why is this? This is because of ion polarization, because magnesium is the smallest one, so it polarizes the carbonate the most. But as we move down the group, the size gets bigger, and as a result, the ion polarization is decreasing. And as the ion polarizing is decreasing, that the carbon-oxygen bonds getting stronger and stronger. And as a result, we need a more amount of energy to break it. Now, is it understandable? Okay. Now, what they are saying Yet you have to take a look, you have to uh, use these sizes to explain this, that why it becomes more endothermic. So if you see that the size of oxide is very small as compared to the size of carbonate ion, isn't it? The size of oxide is relatively very small than carbonate ion. Is this understandable to all of you? Now, try to think that see this is statement that the enthalpy change of metal carbonate and enthalpy change of lattice energy of metal carbonate and lattice energy of metal oxide changes by different amounts. So see here, this is very smaller size. So if the size of magnesium, for example, and after magnesium, we have a calcium, a bigger size. So when these two bonds and when these two bonds, so due to this bigger size, the change is significant among the sizes. But when we talk about a carbonate, carbonate is already a bigger, very big in size. So when magnesium bonds it with it, the total size of both the ions, and when calcium bonds with it, the total size of both the ions, their change is not that significant as the change that was significant over here when a metal cation bonds with the oxide ion. Is this understandable? Is this point is clear? So as the size, the change in size is significant, so we can write there that uh, the change in lattice energy of metal oxide is more significant or the change is more as compared to enthalpy change of, or sorry, lattice energy of metal carbonate. Is this clear to all of you? Now, if I try to explain this thing graphically, then I think it will be more understandable for you. Uh, See, here we get metal carbonate. On decomposing, it turns into metal oxide and carbon dioxide, right? And here I have a metal ions, carbonate ions, and oxide ions. So metal ions and carbonate ions are producing this, and metal ions and oxide ions are producing this. So if the metal gets changed, Then see what will happen. This, let me write over here. For example, this is magnesium, right? So here I got magnesium, here I got magnesium carbonate. Okay. Now instead of magnesium, I use a calcium. Calcium has a bigger size. So what will happen? That as carbonate is very big, so the change from magnesium to calcium is not that big. So there is a slight change in the formation of calcium carbonate. Is this point is understandable to all of you? See, this value is a little more greater as compared to the magnesium carbonate. But the oxide ion is very small, so the change is relatively significant. So here the magnesium oxide, when the calcium oxide is formed, the change is relatively very bigger. That's what we have concluded. See, this change and this change, the change is very bigger. If you look at this change and this change is very smaller. So see what happens to the magnitude of calcium decomposition of calcium carbonate as compared to magnesium carbonate. So it becomes more endothermic, right? See here it's the smaller change and here it gets the bigger change. And it is why, because of the smaller size of oxide ion, the enthalpy change or the lattice energy of oxides changes with the bigger value as compared to the enthalpy change or the lattice energy change in the carbonates. Is this understandable to all of you? Okay. Now, next part. C. Potassium sulfite K2SO3 is used as a food additive. The concentration of sulfite ions SO3 2 negative can be determined by titration using aqueous acidified manganate ions. Okay. A 25 centimeter cube solution contains 3.40 gram of impure potassium sulfite. Okay. Okay, so this is the volume and this is the mass of impure potassium sulfate. 25 centimeter cube of this solution requires 22.4. Okay, now see, here you guys or some of the guys do the mistake. See, initial volume of K2SO3 is 250 and the mass is 3.40 gram. So from this 250, 25 centimeter cube is taken out, and for this 25 centimeter cube, 22.40 centimeter cube of manganate has been used, and the concentration of that manganate solution is 0.0250. Is this understandable to all of you? That how the reaction has been performed? Okay. The reactions occur as shown by two half equations. Okay. Give the ionic equation for the reaction between sulfide and manganate. So see, there are two half equations. And if you see the two half equations, we know that this is an oxidizing agent, right? So if it's an oxidizing agent, it must undergo reduction, and sulfide in this case must undergo oxidation. Is this understandable to all of you? So if you see here, isn't it oxidation is taking place? Because if you look over here, this sulfur has an oxidation number of +4 because there are three oxygens, which makes it -6, and the net charge is -2. And if you work over here, this oxygen has an oxidation number of +6 over here, because there are four oxygens, which makes it -8, and the net charge is -2, which means it's +6. So see, it has been oxidized, and there is another evidence that two electrons are lost from here. That's why they have written individually. The electrons are written separately, which means this is the oxidation. Is this understandable? And if you see over here, the electrons are on the left side, and on the right side, we don't have any electron, which means the electrons are being added and the gain of electron is reduction. Is this clear to all of you? Okay, then in this, now what we have to do, we have to just add both the equations. But before adding, we have to balance the electrons in both the equations. So what I will be doing, I'm going to multiply the first equation with the 5. So if I multiply it with the 5, so it will become 5. There would be a 5 water, 5 SO3, 2 negative ions, 5 SO4, 2 negative ions, 5 times 2 makes it 10. And the electrons will also become 10. Is this clear? Now, I will multiply the second equation with the 2, which makes it 2. 2 times 8 makes it 16. 2 times 5 makes it 10. Here I get 2, and here I get 8. Is this understandable? Now, what I need to do, I have to add them, but before adding, I have to cancel out the same things which are on the opposite sides of the equation. Because we have to make the number of electrons equal. So see, if I multiplied the first equation with 2, there are 10, that there are 10 electrons. If I multiplied the second equation with the first equation with the 5 and the second equation with the 2, makes the number of electrons equals in both the equations. That's why we did it. Yes, Abdullah, is this clear? See here. If you see, there are 2 electrons. So that's why I multiplied this equation with the 5, because instead of 2, now we have a 10 electrons. And here, see, there are 5 electrons. So if I multiply it with the 2, I will get a 10 electrons over here. So we multiplied the equations with the different, with 5 and 2 to make the number of electrons equal in both the equations. Is it clear now, Abdullah? Yes. Is it clear to all of you? Now, what I will do, I will just add both the equations by after removing the things which are same on both sides. So there are 10 electrons. So I will remove the 10 electrons on both the sides. Now, if you see, there is a water on both the sides, right? There are 8 and there are 5. So 5, and instead of 8, we are left with the 3. Same. There are 16 hydrogens and 10 hydrogens. So 16 and 10, and here we are left with the 6 hydrogens. Now, if you will write the equation, so it would be 2MnO4 negative is reacting with 5 sulfite ions. 6 hydrogen ions are there, forming 2Mn2 positive plus 5 sulfate ions plus 3 moles of water. Now, is it clear to all of you? Just give me a minute, please. Okay, sorry. Now, what they are asking you to calculate the percentage purity of the sample of potassium sulfite. Okay, show your working. So see that they have already told you that it's 3.40 gram and which is impure, right? So we have to find that in this 3.40 gram of impure potassium sulfite, how much is the pure? How much mass is pure? See, that's what they have given you over here if you read. So we just made this scheme over here that how the reaction is taking place. So if you look at this, we got the moles, we got the volume of magnet and we got the concentration of magnet, right? So from that concentration and volume, we are going to calculate the moles of magnet. So the moles of magnet equals to its concentration, which is 0.0250 mole per dm cube times volume, which is 22.40 centimeter cube. So I have to divide it with 1000 to turn into a dm cube. Can anyone calculate and tell me the answer, please? Okay, Ahmed, thank you. So the number of moles which I have found over here is 5.6 exponent minus 4. So these are the moles of magnet. Now, from these moles, I have a balanced equation and I have the ratio. So I can able to calculate the moles of sulfite ions, right? So I'm going to take the ratio between magnet ions, moles of magnet ions and the moles of sulfite ions. So the ratio on in the balance equation is 2:5. So if the magnet ions, the moles of magnet ions are 5.6 exponent minus 4, then the moles of sulfite ion would be x. So if I calculate the x, so x would be equals to 5.6 exponent minus 4 times 5 divided by 2. Yes, can anyone tell me the number of moles of sulfite ions? Okay, thank you, Ahmed. It's 1.4 exponent. Ahmed, can you check its exponent minus 3? Yeah, it's exponent minus 3. So see, these are the moles and these are the moles of sulfite ions. Till here, is this clear to all of you? Now, if I ask you, in which volume of these moles are present? Yes, can anyone tell me? These moles that we have find over here. Yes, very good, Ahmed. See, these moles, because this much volume of magnet reacts with 25 centimeter cube. Yes, very good, Mariam. Very good. So the moles that I have identified over here is actually present in 25 centimeter cube, isn't it? But the total potassium sulfate is present in 250 centimeter cube. So I have to first figure out the moles in 250 centimeter cube. So now I got the ratio that 25 centimeter cube has 1.4 exponent minus 3 moles of sulfite ions. So if the volume is 250 centimeter cube, then the moles would be x. And in this case, if you calculate the x, it would be 1.4 exponent minus 2 moles. And these are the moles of sulfite in 250 centimeter cube. Is this understandable to all of you? So now we have to find the mass of potassium sulfate. So for the mass of potassium sulfite, sorry, not sulfate, we need its moles multiply by its MR. So the moles of potassium sulfite would be the same 1.4 exponent minus 2, because if we have dissolved 3.4 gram of the whole sample. So if you see the formula, it gives only 1 mole of potassium sulfite gives you 1 mole of sulfite. So whatever the moles of sulfite I have identified. So that's what we did, Hamad. The moles of potassium sulfite would be the moles of sulfite that we have found in 250 centimeter cube is the moles of pure potassium sulfite. So these are the moles. Can anyone calculate the MR? 1.4 exponent minus 2 times MR of potassium sulfite. If I'm not wrong, potassium is 39.1. Let me see. We got a periodic table at the end. So 39.1. You are wrong, Ahmed. 39.1. So it's 78.2. 2 potassium, 78.2. 78.2 and then 32.1. 78, 80. 120.3. And then we have a 3 oxygens as well. So 48. Yeah, 158. Thank you, Hamad. So the MR is 150.8 for potassium sulfate. So if you multiply them, you will get the mass, and that is the mass of pure potassium sulfite. Can anyone tell me the mass? Yes, can anyone multiply it and tell me the mass? 2.2162 grams. Okay, so this is the mass of pure potassium sulfate, and impure has a mass of 3.40. So if I have to find the percentage, 3.40, and the mass that we have identified is 2.2162 divided by 3.40 multiplied by 100. Can anyone solve it and tell me the answer, please? It's 65.2%. Okay. Now, D part. Potassium disulfide K2S2O5 is another food additive. The disulfide ion has the displayed formula shown in figure 1.2. Reduce the geometry around the sulfur alpha atom in S2O5. So if you see over here, how many bond pairs are there around sulfur? Can anyone tell me? There are 4 bond pairs. Yes, very good, Abdullah. Very good, Shahan. See, when we are going to decide the shape, remember the 2 bond pairs, these are 2, 2, we are going to consider them 1. So there is a 1 bond pair over here. There is a second bond pair over here. There is a third bond pair over here. And there is a 4th bond pair over here. No, Shahan. If you look at sulfur, sulfur belongs to group 16 or group 6, isn't it? So it means sulfur has how many valence electrons? There are 6 valence electrons, right? Is this clear to all of you? So if there are 6 valence electron, but if you see, if we look at this sulfur, one electron is shared over here, one is over here, one is over here, one is over here, one is over here, and one is over here. So how many electrons are shared? All 6 electrons are shared. So it means there is a no lone pair. There are 4 bond pairs and no lone pair. Is this understandable? And if this is the case, then the geometry is tetrahedral. The shape is tetrahedral. And the bond angle is 10. What you have written the bond angle, Shahan? Let me see. It's 107, I think. Yeah, it's 107. They have a more electron charge density, Shahan. But if you guys recall, I think I have shared the AS notes with you guys or not? I will share the bonding uh the chart with you guys if where it is. See, you guys need to remember this thing. Yeah, it's 109.5. My bad. Sorry. Thank you, Mariam. Yeah, whenever the shape is tetrahedral, it's 109.5. And 107 is when a trigonal pyramidal. 109.5 degrees. So the geometry around over here is tetrahedral. Okay. Shahan or anyone of you, can anyone take the screenshot of this one and share it in the past paper session group? So everyone got to review about the bond angles and shapes. Now, is it clear to all of you? Yes, if anyone of you has any query regarding this, any confusion regarding this, please ask. Okay. So we are keeping the session here, and I'll try to do one more class tomorrow. And if we'll do the class tomorrow at 9 or 9:30, is it fine for all of you? In the midnight. Yeah, it's 12 midnight. Oh, sorry. Yeah, 9 or 9:30 midnight. Yeah, 9:30 p.m. Okay, so we will be doing one more class, inshallah, tomorrow at 9:30 p.m. Okay, or it's 9 or it's 9:30. Okay, so see you everyone tomorrow. Take care. Allah Hafiz.